and welcome to the Warren County Community College Small Unmanned Aircraft System Drone Program, class number 4, Weather, Part 1. This lecture will help you in your Part 107 test preparation. We'll cover half of the weather concepts in this video, and in the next video, we'll cover such things as METARs and terminal area forecasts. For this video, we're going to review weather and meteorology. We will talk about wind, fronts, storms, fog, visibility, and clouds. And the last thing we'll cover is probably some of the most difficult concepts for people to understand who are new to aviation, and that's the idea of atmospheric stability and the idea of density altitude. This is a test question you might see on the test. One of the most important aspects in small unmanned aircraft system decision to fly is the weather. In the last class, we covered the National Airspace System, and we talked about the importance of safely navigating the National Airspace System to ensure that unmanned aircraft do not interfere with manned aircraft. And the other consideration that is most important and probably most difficult on the test is the concept of weather. I want to remind you that you may have learned this in an earlier part of your life. Often we cover this in kind of that transitional period between middle school and high school in one of the science classes. You see it every day on TV as you get the weather report, but sometimes what we hear, what we see doesn't really compute until it has to. And that's the goal of this video, to try to bring you up to speed on weather. One of the things I like to remind you is that most weather on the planet really has to do with the power of the sun and the sun's influence. In this, what I mean is heat. So when you are getting into your Part 107 test, if you get to a question and you cannot seem to figure out what does this mean? What is it? I don't remember this. If there's anything related to rising temperature, heat, temperature itself, think heat. Think about the heating of the earth. And if you have to take a guess, guess heat. Because every physical process of weather, change or variation of weather patterns is accompanied by or is a result of unequal heating of the Earth's surface. So what do we mean by this? Let's take another look at a test questions you might come across. What consideration is the most relevant to a remote pilot in command when evaluating unmanned aircraft performance? Is it weather, the ground crew, or the type of operation? The answer would be weather. Every physical process of weather is accompanied by or is the result of a blank. Is it the movement of air, pressure differential, or heat exchange? And again, if you got this question and you weren't sure, always go, if you got to take a guess, and that's never a good thing, so you should study, but if you have to take a guess, heat will be the answer. What causes variations in altimeter settings between weather reporting points? Heat. And in this case, the answer would be something along the lines of unequal heating of the Earth's surface. So keep these questions in mind and these answers as you're moving forward. And remember, heat is often the answer. Another question you might see on the test could be something along the lines of this. The development of thermals depends on, and you may be sitting there going, I don't remember reading about thermals, but the answer would be solar heating. So look for that heat when in doubt. We're going to come back to the idea of hot air versus cooler air, and it'll affect weather patterns. But before we get to there, let's talk about wind. And let's remember, obstructions on the ground do affect the flow of wind. If there's big, large buildings in the way, that's going to affect the wind. If you've ever walked through a large city with large buildings, you may be on one street and there isn't any wind. You may go 3 streets over, it may change the building, the roadway could be coming in a different direction, and you could feel like you are in a wind tunnel. And you've seen this because the obstructions of those large buildings affect the flow of the wind. Same thing happens when you're flying a drone, those obstructions, would they be on the ground? They could be trees. They could affect your speed. They'll affect your performance of the drone, your battery life, etc. Obstructions can create rapidly changing wind speed. Also remember when you're taking your test that wind can be an unseen danger. You cannot see wind coming. I mean, you may see tree movements, but it depends. If you're not in a rural area with a whole host of trees or suburban area, but if you're in a more urban kind of environment, there may not be that many trees and the buildings aren't going to move. So remember, wind is a danger you may not see. You may also have different wind conditions at higher altitudes than lower altitudes. Remember that high winds influence the geographical position in flight. So winds can move your drone. They've gotten really, really good at countering wind speed. And we've flown drones here at Warren County Community College in winds as high as 20, 25 miles an hour. I don't like to go that high. I usually like to postpone that mission. The drone can do it. Often they've gotten very good. But remember, you're going to run through the battery really quick, so you may not be able to fulfill the mission. Because wind influences battery usage in life. If the propellers have to turn faster on a quadcopter or a hexacopter, then in order to counter the wind, then that battery is going to be used more. If the propellers on a fixed wing, have to move faster, or more often because the wind is affecting the flight of the drone, then that's going to affect your battery usage and your battery life. So there are two basic wind patterns. There's the cyclonic circulation, and there's the anticyclonic circulation. So the cyclonic circulation, we can see, happens during low pressure and goes in a counterclockwise. Anticyclonic, which is the outflow of cold, stable air at the top, happens in high pressure systems, and it is a clockwise pattern. So cyclonic circulation is when the air flows toward a low and is deflected to create counterclockwise circulation. Anticyclonic, the opposite. The flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. You can again see the concept here. Now, remember the basic laws of physics. Hot air rises, cold air falls. So the unequal heating of the Earth. So as the Earth shifts on its axis and rotates around the sun, we know this as seasonal changes. Gets warmer in the summer, colder in the winter. Those months may vary based on where you are on the planet. But we do know that hot air rises, okay, and we know that this happens in low pressure. We know that the air spirals upwards anti-clockwise at lower levels and then flows out when it reaches the atmosphere. And we know that air generally tends to flow toward low pressure. So in the opposite one, when the blue representing cold and red representing hot, cold air sinks because as hot air rises, the cold air comes down. This is high pressure. And the air spirals out at a clockwise at low levels. So here we get the idea of this convective current, if you will. So this is when two pressure systems come together. Low pressure system with warmer air and high pressure systems with colder air. And you'll see that the wind, when the two fronts come together, the cool surface, warm surface, cold air stays to the ground. Warm air goes over top of cold air, and we'll talk about this. But as they come in, you get what's known as the convective current or convection current, because the warm air is lighter, it's less dense. And then we'll come back to this when we talk about density altitude, but think about it. You know that Mile High Stadium in Denver is one of the hardest places to play football because you're a mile up, so there's more warm air and the air is thinner there. So you don't get as much oxygen when breathing in. Well, this also affects aviation as warm air rises. And if we think about this, if the air is less dense and we have a quadcopter and we're up high, it will have to spin its propellers more to stay in the air because it doesn't have that dense air that it's flying on. It's got a lighter air, a less dense air. So these systems matter. As they come into connect with each other, these two fronts, there can be violent things. So we know this. We know this happens in the summer months. If you've ever experienced a thunderstorm, it gets hot, it gets muggy, then you get a very violent storm, and it usually is followed by cooler air coming in. And there's usually, as thunderstorms come in, a lot of wind that starts to come in. So when we talk about convective currents, these are currents that cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. Convective currents close to the ground can impact the pilot's ability to control an aircraft. For example, if they're coming in for a final approach, the rising of the air from the ground, devoid of vegetation, sometimes produces a ballooning effect that can cause a pilot to overshoot a landing spot. So the air could be pushing the aircraft up a little bit so you go past the landing spot. And so if you are in an approach over a large body of water or an area of thick vegetation or forest, this can create a sinking effect that can cause an inexperienced pilot to land short of the landing spot. So in other words, the air is pulling the aircraft to the ground. Get a little bit of a sense of this in terms of wind when we talk about downdrafts. And so you may have heard the term headwind and tailwind. So remember that if there's a strong downwind, all right, so the plane is taking off at position 1. At position 2, it hits the downwind. It can actually push an aircraft down. And the same can happen to a drone that can happen to a manned aircraft. So you want to be aware of downdrafts. You want to be aware of their impact on aircraft. And they may, in fact, be strong enough that they can overcome the power of the plane or the drone's engine. And this is important to keep in mind. So you also want to remember that these downdrafts, headwinds, and tailwinds are accompanied sometimes by wind shears. And wind shears are a sudden, drastic change in wind speed and or direction over a small area. So you can feel in the one area, if you look at our example again there, 1, 2, 3, 4, that everything's fine for takeoff, and then you hit that, and then you realize you have a problem, and it's probably too late. Low-level wind shear is commonly associated with passing frontal systems. So when those two temperature systems, low and high, hot, cold, come in together, there'll be thunderstorms and temperature inversions with strong upper-level winds. And we'll talk a little bit about this in a minute. The other thing you want to remember about wind is that obstructions can matter. Obstructions on the ground, such as mountains or skyscrapers, can break up the flow of wind and create wind gusts that change rapidly in direction and speed. Before flying in or near mountainous areas, try to get information from an experienced pilot or flight instructor. Here is where you might lose a drone. So let's think about this for a second. Notice, and Warren County Community College is right next to a mountain, so we do get a lot of weird wind patterns here, which gives our students great practice. But you have to know that if there's wind coming from the left to the right here, but there's a mountain in the way, the wind cannot go through the mountain. It has to go over top, which means it can cause these patterns of wind here that can be quite turbulent. It can have mountain waves. It can have breaking waves in the air. All of this wind trying to get up over the mountain will affect. So if you're way up high here, away from the mountain, you're probably fine. But the closer you get to skyscrapers, structures, mountains, you're going to be impacted by the wind and by wind shear. So you want to keep that in mind as you go out there. You can even think about airports this way. There's a lot of buildings around runways and airports, and they can impact takeoff and landing. So this is why takeoff and landing is often the most dangerous. It's why you want to check your weather patterns. It's why you want to check your wind gusts. It's why you want to be, as a professional pilot of unmanned aircraft, taking the same things into consideration that a manned aircraft pilot would take in. You also want to be aware there are microbursts that can happen. A microburst is associated with corrective participation. It occurs in a space of less than a mile horizontally and within 1,000 feet vertically. It's important because this might be on the test. It lasts about 15 minutes. So microbursts last about 15 minutes and can produce downdrafts up to 6,000 feet per minute. So this can dramatically affect manned aircraft. Now, this will really affect unmanned aircraft, especially small quadcopters or small unmanned aircraft, because they really don't, at this point, do well in weather. So keep this in mind. You can often see them coming, but microbursts are important. They have both rain and wind and storming in effect. So remember, wind can affect small unmanned aircraft system performance and maneuverability during all phases of flight. So landing, takeoff, hovering, anything you're doing, wind can affect. You may experience different wind speeds and impacts at different levels of altitude. Obstructions on the ground, remember, can affect the flow of wind and may create rapidly changing wind speed and direction and are an unseen danger. High winds can make it difficult to maintain a geographic position in flight and may consume more battery power. That's one of the things you'll remember, want to remember especially, is they'll often use the word, instead of battery power on the test, they'll use the word performance. It affects the performance, meaning the efficiency and the effectiveness of the aircraft. Local conditions, geological features, and other anomalies can change the wind direction and speed close to the Earth's surface, making it difficult to control and maneuver your small unmanned aircraft. Unmanned aircraft often have limited performance and therefore high wind conditions. This small unmanned aircraft system, or sUAS, may consume more power to maintain position or other maneuvers than in calm air. Calm air, straight, steady flight, greatest battery. You will get the most out of your battery. Every turn, every altitude shift, wind consideration, that will all consume more battery power, which is why it's often difficult to know how long a battery lasts, because it really depends on these wind and weather features that you will be flying through. If the wind is strong enough, the sUAS performance might not be able to adequately counter the wind, making it not nigh impossible, but impossible or difficult to fly back to your position for recovery. So be aware that you may have flown a mission, and you may fly a duplicate mission on a different day, and you were perfectly fine one day, but because there was more wind on the second time, you may not be able to get back. So you want to keep these things in the back of your mind as a pilot, because you want to be safe and effective. You should also know that there is wind shear. We talked about this a little bit before. Wind shear is that sudden drastic change in wind speed or direction over a small area. Wind shear can subject your small unmanned aircraft system to violent updrafts or violent downdrafts, as well as to abrupt changes in the horizontal movement of the aircraft. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the proximity of an aircraft to the ground. So if you got a huge downdraft that pushed your drone down and you were close to the ground, you could end up crashing. If you were a little higher, it would probably impact your drone. It would move it in the sky. But if there was nothing to run into, then you wouldn't have a problem. But think about it if you're doing something in a more urban kind of city environment. Wind shears next to buildings could be quite hazardous. This is why they don't let drones fly over people. Wind shear can exist where? Might be a question you see on the test. And remember, it's at all altitudes. Where is it most dangerous? The closer you are to the ground. Now, you've seen this every morning if you watch the news, but you may not see it enough. You may not think about it when you see it. So the best way to kind of remember this, and you may get a question or two about fronts. Cold front. Look at that blue with the upside down triangle. What I like to tell students is think of that as an icicle. That'll remind you ice is cold, right? So that's the cold front. Warm front, think of that as an upside down sun or half the sun. Sun is hot. Red and blue also help you remember, blue being cold, red being a color that denotes heat. Okay, and you also have symbols for stationary fronts, occluded fronts, a trough, a ridge, a squall line, and you won't see dry line or tropical wave on the test, but know that they exist. So this is what this might look like. Okay, air masses and fronts. That's a body of air that comes to rest on or moves slowly over an extensive area. A ridge is an elongated area of high pressure. So let's start to look. So you have high pressure, high pressure, high pressure, high pressure. So here's a low pressure. Okay, the closer these little lines here around the pressure system are to each other, the higher the wind speed. You can see your cold front here, the icicles. You got a cold front here. All right. And you got a warm front. So weather is moving all the time. This is a weather map that gives information, but you have to look at it carefully and consider what it's saying. So here, high pressure, hot air is moving in. A little bit better here. So see, this would be a very windy area. Here would be, they would be telling you high pressure. You can see the front. This is a stationary front. We know that because it goes back and forth from warm to cold. Then there's a cold front, stationary, warm front. Okay, the low is out here, and the high pressure is right here. There's a low down here. So these will, again, they're going to tell you weather forecasts, weather patterns. You hopefully know that the green here represents storming. So not surprising when the high pressure system is coming in, you're starting to see much greater levels of storm formation. When there's low pressure, you see much less. So these are things, again, to keep in mind. You also want to know that a trough is an elongated area of low pressure. Boom, right here. All fronts lie in a trough. Okay, so look at this spread out area right here between these two white lines here. Okay. So you also want to know that cold fronts are often accompanied by poor weather ahead of the front, which passes quickly. Okay, so you know this again. Let's try to remember. When the cold front comes in, all right, it's pushing underneath, because it's colder air, underneath higher warmer air. So the warmer air is going up, the colder air is staying close to the ground, and it's going to come in and it's going to have poor weather ahead of the front, but it's going to pass quickly. So we know this in these thunderstorms, these summertime thunderstorms. You know, if you've ever tried to go to Disney World in Florida in the summer, you're probably at every day going to see that thunderstorm come through. That's usually when people go back to their hotel and then switch whatever they're going to do for the rest of the day. So they come in almost daily. If you've ever been down there and you've experienced that, you know what I'm talking about. But they move rather quickly. So maybe there for an hour, hour and a half. That's what you're going to see when a cold front comes in. So you see it here. It's pushing that warm air up. Cold air coming in, pushing that warm air up. Once a cold front has passed, you can expect the wind to shift and turbulence due to increased wind speeds. More severe cold fronts often produce thunderstorms, hail, and tornadoes. This is a fun fact. I used to teach research, so one of the things that we used to do is say, can you find the strangest research that's ever done? And there was one. When dealing with tornadoes, a solution to tornadoes would be the detonation of a thermonuclear bomb. The government once paid people to study this. This was the closing line, but the effect of the devastation might not prove viable to the deterrence of a tornado. In other words, the devastation of using that to stop a tornado would be worse than the tornado itself. And that kind of shows you the power of, although being funny, that shows you the power of weather. We cannot counter weather. There's no way to stop it. Whether it's aviation or science, the weather patterns, they're going to impact. And you know this from the natural disasters that have occurred. And they've become more frequent because we're seeing even more of that heating of the earth. So this is an important thing to remember. Warm air rises, cold air comes in. So let's talk a little bit more about this. Here you get a sense of that in this picture. Okay. This is when a warm front comes in. So it's going to be the opposite. Warm fronts move about half as fast as cold fronts. They're often preceded by low ceilings, increased participation, in other words, increased rain, and reduced visibility. Okay, so there's more precipitation here, more rain as the warm air moves in. Okay, and it brings its cloud cover. All right, since warm air goes over the cold air, it pushes it to the ground. So this is your long periods of rain, multi-days of rain. If you're experiencing multi-days of rain, a lot of fog, reduced visibility, then what you're seeing is a warm front moving in, but it's going over top of the cold air. Doesn't move as fast because of the angle here. It can't push the cold air out of the way. Where the cold air, if we pretend like it's going in the opposite direction, is going to push the warm air up, and that's where you're going to get your thunderstorms. Frontal changes are marked by sharp difference of characteristics, and this is fancy term for that is discontinuity. Okay, so what is it that makes a frontal change? When there's a front coming in, there will be a temperature change, okay? Because obviously it's warm air versus cold air one way or another. So you're going to see a change in temperature as the front moves through. A continuous decrease in pressure followed by an increase as the front passes. So that's what they mean by low pressure, high pressure. And you're going to see a shift in wind direction, wind speed, or both direction and speed. You also want to remember there are surface weather maps. They provide information about fronts, areas of high and low pressure, and surface winds and pressures, basically for each weather station around the country. And most of the major airports will have, obviously, because it's so important to them, good weather. So these little lines here that were white on the other, these are called isobars. So that's what your isobars are. They're going to, again, tell you kind of wind, speed, direction. These lines here, this is a cold front. We remember that because it looks like icicles. There's a warm front because they look like suns. This is a stationary front because it goes back and forth. You're going to have your high and your low pressure. Okay. And this gives you some radar pictures as well. So weather maps can be very effective in kind of giving you an idea of what the weather pattern is for the day and what it's going to be coming through. When we're flying drones, we do need to be aware of clouds and the effects of clouds. So, you know these clouds way up there above 23,000 feet, cirrus clouds, okay? And they're nice little clouds, don't cause any problems. But you never fly up at 23,000 feet. So you know they know that there's clouds that occur between 6,500 feet and 23,000 feet, roughly. And these are here. You don't really need to know these either because, again, you don't fly there. But you should have some idea of clouds closer to the Earth. So those, because that's where you'll be flying. So there's cumulus clouds. There's stratus clouds. There's stratus cumulus. And this is called cumulonimbus. Yes, you see the word here, and you can tell that I, for some reason, cannot pronounce words today. So precipitation, not participation like I had on that other slide, precipitation is showery when a thunderstorm. So this cumulonimbus is a thunderstorm. and we're going to come back to this in a minute. You see the lightning? That's how you know it's a thunderstorm. Nimbostratus comes when, so these come when a cold front is pushing a warm front. So the cold air is coming in and it's pushing everything up. That's why this cloud is so like a column, all right, and so large. And we're going to come back to this because this is a thunderstorm and you need to be aware of this for both the test and for your flights. Nimbostratus is when a warm front comes in and pushes to the ground. Here you're going to have steady precipitation. I'll laugh at myself today. Sorry about that. This is again when the warm front is pushing the cold front out and pushing it to the ground. And this is when you're going to get several days of rain in a row. That's how you can kind of tell. Thunderstorms more violent because happening very quickly. Cold air pushing warm air out. And I'm going to try one more time. Cumulonimbus. Thank you. Cumulonimbus. There you go. That'll give you a better sense of that. So this is going to be on the test. And it can be a little bit hard to remember. You need to memorize this chart. You can find this chart right here. You can find one a little bit more clear all over the internet. But this is about atmospheric stability. Because small unmanned aircrafts always fly at low altitude, because our legal limit is really 400 feet, it might not seem important, but the stability of a local air mass can have a significant impact on ambient conditions. Unstable air can result in weather conditions that are unfavorable to small unmanned aircraft operations. A stable layer of air would be associated with a temperature inversion, a condition in which warm air is situated above cool or cold air. In other words, moving in, that warm front is getting pushed out by the cold front. That's where you're likely to get a thunderstorm. Warm air below, on the other hand, decreases the stability of an air mass. And this can be a little bit confusing when you first think about it. All right. So unstable air is when the warm front is pushing the cold front out, but it's also pushing it towards the ground. That's when you're going to get a lot of showers. You're going to get unstable air. It's going to be rougher air, more turbulence, and good visibility you get, though, except when there's blowing obstructions. That's known as unstable air. Stable air, okay, this is where you're going to get more clouds, continuous precipitation, smoother air, but fair to poor visibility in haze and smoke. So showery precipitation versus continuous precipitation. You want to kind of get yourself ready for that, and you'll see and when we do some practice test questions how that works, and it'll become a little bit more clear. Visibility in clouds. Good visibility and safe distance from the clouds enhances the remote's pilot ability to see and avoid other aircraft. So there are some standards. And those standards you want to memorize. You are required by law before each flight to determine that visibility from the control station, in other words, your remote control where you're standing, is at least 3 statute miles. That's what the SM stands for. And that the U.S. is Unmanned Aircraft System, or the unmanned system, is kept at least 500 feet below a cloud and at least 2,000 feet horizontally from a cloud. These are requirements. They're not best practices. So what does that mean? So you want to start to remember that. Visibility, 3 statute miles, always 3 statute miles, and you need to keep your drone 500 feet below a cloud and 2,000 feet horizontally from a cloud. These tend to be standards that are used for many answers. So you want to stay 2,000 feet from guy wires. You want to say 2,000 feet horizontally from a storm coming in, but always 500 feet below a cloud. So if your cloud cover is at 500 feet above the ground, you can legally fly a drone 400 feet, but you have to keep that drone 500 feet below a cloud so that if there's a manned aircraft coming out of a cloud, it would have time to see you and divert, or vice versa. You would divert out it its way. That would be hard to do if there isn't at least 500 feet. So really, to fly to 400 feet in the air, your cloud cover has to be at least 500 feet in altitude or above. So if your cloud or 900 feet rather, and above. So to give you an example, you have to be able to subtract the 500 feet. So if you went out to fly a mission and you needed to fly that mission at 200 feet, but the cloud cover was at 600 feet, you would not be able to fly that mission, because you'd only be able to fly to an altitude of 100 feet, because you would need to keep that 500 feet between your unmanned aircraft and the cloud. So 900 feet will get you to your 400, because you subtract 500 from 900, 400 is left. If you're at 700, then you can fly to 200 feet. If the cloud cover's at 800, you can fly legally to 300 feet. But there has to also be 3 statute mile visibility, and you have to stay 2,000 feet horizontally from a cloud. This can be hard to kind of figure out, but luckily there are a lot of apps out there. We went over it in the first video, which will tell you whether you meet these conditions or not, and it will help you understand this. So which clouds are below 1,200 feet AGL, or above the ground level? Probably your lower clouds, like your nimbostratus or your towering cumulus cloud, cumulonimbus. Starting to be able to say them again. All right. So keep in mind, some clouds are at the bottom. This cloud has vertical development. This is a thunderstorm cloud. So let's also talk about cloud cover. Again, you have to have 3 statute miles of visibility. You have to be able to see for 3 miles. You have to be at least 500 feet below a cloud and 2,000 feet horizontal from a cloud. When you don't have an app to tell you, you need to use a known object to measure the visibility and height. If you're like, well, how do I know? You should choose the most conservative estimate. Remember, safety first, always safety. And never operate an unmanned aircraft in fog or above a cloud. And why is that? Well, remember, fog is a cloud. So you should be, if you're staying 500 feet from it or 2,000, you can't fly in a cloud. But think about it like this, if you watch my mouse. You don't know, there could be an airport under here. And if you're flying above a cloud, there's no way for you to see manned aircraft, even if you're standing on this mountain, and there's no way for manned aircraft to see you. So this is a very dangerous situation. So you would not be legally allowed to fly here. So there can't be clouds below you ever. And you have to maintain that 500 feet this way and 2,000 feet this way. So there's not 3 statute miles. There might be 3 statute miles visibility, but the other restrictions are going to be there for you. I'm not even going to guess what just happened there. So we'll go back to our cloud cover. All right. In cloud cover, it is imperative, means it is so important that the unmanned aircraft never be operated in an area with an obstruction to visibility, such as either smoke or clouds. You must be able to maintain visual line of sight. Remember, VLOS, visual line of sight. That is regulation, law. You must always be able to see it. So you have to know. So you can see here, if you're doing a cell tower, you may be well above 400 feet. In a cell tower. But if there's clouds below it, or there's fog, you can't be on the ground and see that drone in the air. So you need clear sight lines. And the remote pilot in command has to always maintain that. That is a very serious rule for safety. So what is the minimum visibility for small unmanned aircraft system operations? 3 statute miles, 500 feet below a cloud, 2,000 feet horizontally from a cloud. These are numbers you are going to want to memorize. What's the minimum distance from clouds required for small unmanned aircraft Part 107 operations? That is 500 feet below, 400 feet horizontal of the clouds. So these, again, I cannot emphasize enough. Number of questions on with these kinds. Sometimes they'll ask you to do a little math. Remember, when you take the test, they give you a little calculator with the electronic system. But keep this in mind, very important. Now, let's talk about thunderstorms. 3 conditions necessary for a thunderstorm to form are: there has to be water vapor. It has to be sufficient. Okay, you can't have a thunderstorm without liquid. There has to be an unstable lapse rate, and there has to be an initial lifting force. So let's talk a little bit about this. So let's look at this thunderstorm. All right, so the cumulus stage is when there's something pushing the water particles, the water vapors, into the sky. So there's strong updrafts at this point. And this will be normally when a cold front moves in and pushes warm air up. Well, when it pushes warm air up, whatever's in that air is going to go up. So you know that there's dust in the air. If you've ever seen the sun come through a window, you can see those kind of particles of dirt, dust. And there's also water particles. You know this now if you've gone through the coronavirus. Why do people wear masks? Because we're constantly spreading water vapors through the air. And they're there. They're in the air at all times. So in the cumulus stage, that is when the air is being pushed up. In the mature stage, which is the most violent stage, you have both updrafts and downdrafts. So there's still cold air pushing up, but as it gets up here, this dirt and this water freezes, okay, and then starts to fall. It becomes too heavy to be held up. And that's where you start to get this heavy, quick precipitation that often is associated with a thunderstorm. And this updraft, downdraft is where you're going to get this violence that causes a lightning. Now, keep in mind, this is called an anvil out here. And what happens is these ice particles normally go back down, but they go through the cloud, so they turn back into water vapors. When they're out here and there's not these updrafts and downdrafts, this is where hail comes from. You got these heavy ice particles and they just drop to the earth because of gravity. So what you're seeing is this is the part where hail comes from. Try to look for these clouds before you take the test. You can often see them, especially during the summer months. You may have never noticed how tall they are, but if you're far enough away, you can often see an anvil and you'll start to see these clouds and you'll start to understand them better. There is a freezing line the higher we go away from the earth, because remember, the sunlight rays are coming down, they're warming the surface, and the hot air is coming up. That's those inversions we talked about. Now, at some point in the stage, you're going to get to the dissipating stage, and that is where it's complete downdraft. This is the end of the thunderstorm. The ice particles are falling through the cloud. The anvil is gone. It's not the most violent. It's not the most troubling part, but it's still dangerous because it is a thunderstorm, but this is when it starts to come back down. The cold front is now in the area. So this is another idea that you'll see, and I'll leave this up so you can take a few minutes to kind of look over both the picture and give you an idea of the different atmospheric levels here. It'll also tell you, there's the violent storms in the sea can be more violent because there's more water to pull up. So remember, in thunderstorms, the lifting force from below can be heating from below. Okay, so the earth can get so hot, it's pushing the hot air up. It can be the frontal lifting we talked about, where the cold front pushes the hot air up. Or it could be by mechanical lifting, and this would be similar to a wind blowing air up a mountain. All can push these particles and water vapors into the sky and cause a thunderstorm. So the other thing you want to remember, because there's test questions on it, is there's 3 stages of thunderstorms. The cumulus stage, this is continuous updrafts that produce low pressure areas. There's the mature stage. These have both updrafts and downdrafts inside the cloud. And there's the dissipating stage, characterized by downdrafts. All three will exist. Lightning is always associated with a thunderstorm. It's not a thunderstorm if there's not lightning. So when those clouds are coming together, the updraft, downdrafts, that's when you're going to get lightning. And the more frequent those thunders, the more severe. So you might remember this as a child. You might have been afraid of thunder. You might have been afraid of lightning. And you would do that counting exercise. You would hear the thunder or see the lightning, and you would count between, and then you would be able to kind of figure out how far away it is, how severe. So same kind of concept here. You should immediately complete all drone operations. Drones do not do well in a thunderstorm. But remember that squall line thunderstorms produce the most dangerous conditions for small unmanned aircraft systems. Here's a picture of a microburst. And you've seen these, maybe not quite like this one. You probably have to live in the Midwest, in the flatter parts of the country, to see something like this from such a distance. What is the expected duration of an individual microburst? And we went over this before. And it's seldom longer than 15 minutes from the time the burst strikes the ground until it is over. So in other words, until we get to that dissipating stage. So that's a fast storm. So keep that in mind. If you've flown out and your drone would take 10 minutes to get back, and then this microburst is coming at you, you might be best just to land wherever you are. So kind of keep that in mind. Very dangerous situation. You want to be aware. You want to keep your eye. Remember that the strongest stage for thunderstorms is the mature stage. That's a test question you're likely to get. Okay, so you also can experience icing. Now, you probably wouldn't fly in icing conditions. And you might not be high enough, but you do need to know about this. So you do need to know about structural icing. You need to understand that as ice forms either on your propellers or on your drone, lift decreases. In other words, it's harder to raise up in altitude because your drone has just become heavier. Ice is heavy. The weight of your aircraft increases and stalling speeds increase. The propellers can stall. Because again, the ice is going to be a deterrent. Your thrust decreases, so in other words, your ability to move quickly decreases, while your drag increases, what's slowing it down. So your drone is built with motors for a certain weight, a certain dimension, a certain aerodynamics. And when you deal with ice, you're affecting those. So what you need to remember is lift decreases, thrust decreases, weight increases, drag increases, and stalling speed increases. And they want to remind you also that the effects of icing are cumulative. In other words, if it is kind of a freezing rain situation and ice starts to form, the more water that lands on it starts to create that icing situation as well. We also need to know a little bit about fog. There are different types of radiation and advection fog. You need to know that there's radiation fog. You need to know there's advection fog. You need to know that there is upslope fog as well. And fog is a surface-based cloud. So in other words, when you're on the ground, you see fog, you're in a cloud. It will restrict visibility for your small unmanned aircraft system and your visual line of sight. You can't fly in fog because you can't. You got to be 500 feet below a cloud, 2,000 feet horizontally from a cloud. So there is absolutely no way to fly in fog. But fog is classified in the way that it forms. So there are places that you need to know fog. So there's radiation fog, otherwise known as ground fog. There's advection fog, which is sometimes called sea fog. And there's upslope fog. And this is the fog that would form. You'll see this on the side of a mountain. It's as if a cloud hits a mountain. So let's talk about radiation fog. Also known as ground fog, is formed when the terrestrial radiation or the ground radiation, okay, and radiation here, all things radiate. It is the radiation emitted by naturally radioactive materials on the Earth, including uranium, thorium, and radon. And that cools the ground, which in turn cools the air it is in contact with. So what happens is heat's radiating from the surface at night, cools the bottom air, and then what we get is we get this cloud formation. This fog will form most readily in warm, moist air over low flatland areas on clear, calm, no wind nights. Okay, so you get this fog that forms. That's called radiation fog. You get this advection fog, sometimes called sea fog, is formed when warm, moist air moves. This one needs wind, so ground fog, no wind. Sea fog needs wind to push it over colder ground or water. An example, an air mass moving inland from the coast. Okay, so from this high pressure system is pushing this in, there's moisture here, and it's coming over here, and there's warm. So warmness here, you can see. So it forms this cloud, and that cloud is called advection fog. And then you have upslope fog. This is formed when moist, stable air is cooled to the dew point as it moves up along sloping terrain. And again, wind is required. So basically, you have this moist, stable air being forced up a sloping terrain. The dew point, it's cooled to a dew point, and what happens is fog then again forms. So you'll see this on the side of a mountain. If you don't have mountains, you're probably not going to have any upslope fog. This is the most kind of difficult, and we'll go over this many times outside of this video. And this is this notion of density altitude. So how do you understand this? Well, think of it in terms of manned aircraft, and let's not think of it in terms of unmanned aircraft at this point. There has to be a difference in the density of the air at sea level, which is our lowest level, so at the shore line, than there is at the highest mountains. So think of, again, Denver. Let's think of if you're flying from Los Angeles to Denver, there's a different altitude that's going on. So as you go up in the air density is going to be different. But this can happen not only that way, but when temperatures are going up and down, so when temperature's going up or pressure's going down, you're going to get high density altitude. When temperature's going down or pressure's going up, you're going to get low density altitude. So they have to, in other words, to calculate this, know how much power is going to be needed, know the effects on aircraft, there has to be a standard density, temperature, and pressure from a standard that they can then measure against. So you need to know, and this will be on the test, what the standard is. So the standard is set at sea level, and the standard is 15 degrees Celsius with pressure of 29.92 Hg is mercury. So you need to know this, because what will happen is if you're above that, you're talking about high density altitude. All right. What do we need to know this for? Why do we need to understand the concept in general? Well, on a very, very hot day, the temperature going up, you're going to get higher density altitude. What does that mean? So if you're in a very, very hot summer month, the air at your altitude, wherever you are, may be thinner. So you're experiencing high density altitude. So the idea being you're way up in the air. It's just like being at a higher altitude today because of the air temperature than if we were in a standard kind of day. Same thing happens, low density altitude. That means you're going to get less dense air. So you're going to get a greater performance. High density, less performance. Low density, more performance. Standard, set at sea level, 15 degrees Celsius, 29.9 mercury. This is one of the harder things or concepts for students that I've found over the years. So I am sure I have not done it justice here. We will go over this many more times in the class room environment. That gets us through today's lecture on weather. This was a rather long one. I'm Dr. Will Austin. This is Warren Community College. And again, I've tried to present this to you in the simplest way I can to help you get your initial understanding. The courses in the class and your instructors will also assist you in understanding these concepts, as will additional videos that we will be sending you links to so that you can look at them on the internet. Have a wonderful day.